Okay, so I guess those of you who have gone to lecture exam reviews before know that I don't actually have a planned structure for this, so I'm pretty much just going to answer whatever questions you guys have for a couple hours. So who wants to kick us off? Yeah. Mm-hmm. Yeah. Yeah. So, yeah, that's a good example actually of epoxide stuff. Okay, so 2018 final number 1. Okay, so it says at the top, both form products of formula C10, H18, O2. And then it says show in mechanism and the product for each reaction. Okay, so we got this starting material for both parts. And the only difference between parts A and B is that A has an H plus on the arrow, so it's in acidic conditions, while B has OH minus on the arrow, so it's in basic conditions. Okay, so given that we have an epoxide functional group, I guess like where to start out looking at this, we know we have an OH and an epoxide on here. So you might be thinking, okay, which group do I protonate first? How do I know how that's going to work out? Because we have seen reactions where the OH gets protonated, becomes a good leaving group, and then stuff happens. But between the two functional groups, we also know that epoxide is more likely to be more reactive just because of that strained 3-membered ring that's going on. So I guess what you should sort of be leaning towards and predicting the outcome here is some sort of epoxide ring opening conditions, which is why having H plus here versus OH minus is sort of a big distinction to make. Here we're doing acid condition epoxide ring opening, and the other one we're doing base catalyzed.
Why isn't acid going to open the ring but base?
They both are, just in different ways. So that's kind of what we covered last time. So let me put up like the sort of quick review. So if we take an epoxide and do like H plus and ROH, and let me throw actually the methyl group on there to make it exactly match the example that we saw last time. So we've got an epoxide, we've got an acid source, and we've got an alcohol. So the same 3 components that we have in this starting material, only here, 2 of them happen to be part of the same molecule already. But it's still going to work the same way where we didn't protonate the OH group from ROH. We protonated the epoxide because that's what's going to lead us towards a product where the epoxide ring can actually get opened, and that's what's sort of making the reaction favorable. Okay, so we protonate the epoxide, get a plus on there, and now under these circumstances, am I going more or less substituted for which carbon I attack? More, right? Yep. Because it's under a stronger influence from charge distribution than it is from sterics. So if it's positive charged, in other words, if it's an acid, I go for the more substituted carbon. Okay, so I attack here, pop that open, and get this initially, which I have one more step that I need to do to clean up that positive charge, which is just deprotonate here. I can be vague about it, or I can show maybe like another ROH or something coming in for it. Doesn't matter too much. But that's where I end up getting. Okay, so using the simpler model as basically just a template for the more complicated stuff going on up here, I can just apply the same mechanism and see how that would look. Question?
What are some common acids? Like, is it always written as H+?
Yeah, so I guess there's like H2SO4 is probably the most common acid catalyst, and the reason for that is that it's got the least water in it out of all the concentrated acids. And we know that water might be a problem because then like it might try doing this reaction with H2O instead of ROH. But yeah, like there's a few options, but H2SO4, if I write out the acid at all, that'll probably be what I say it as. So yeah. Okay. So let's start working through this mechanism with acid. I'm gonna sort of get this out of the way a little bit, so I think I should have room up here. Okay, so I go protonate the epoxide. And that gets me to here. And now my ROH can go in, and just like down here, I'm going for the more substituted carbon. So let me just emphasize that on the board here. So more substituted carbon gets attacked, same thing up here. My oxygen goes in, attacks the more substituted carbon of the epoxide, pops that ring open, and here's where I have to be careful about what I'm drawing because I'm making a new ring, so let's do numbering and keep track. Let's say carbons 1, 2, 3, 4, and then the oxygen would be the 5th atom of the ring that's closing down, and then 5 is just now making a bond back onto 1. Okay, so what I'm making is a new 5-membered ring. So let's see, do like that. Okay, so that's 5, 4, 3, 2, 1. Oxygen still has its H, it's positive charged still. Carbon number 1 also has this extra last carbon of the chain that I didn't bother putting a number on coming off of it. And that carbon still has its bond to what's now become an OH. So like that. So you can number these differently or with letters or whatever, just so long as you're consistent about what bonds are being made or formed between them. Okay, so then just to finish this up, we got to do a deprotonation step again, like that. So we should end up with that as the product for this one.
Yeah, that step right there, I was confused. Without any other thing taking the H, you can just grab bond and go feel it.
Good question. So in reality, something would be coming in and taking the H, but we can get real sloppy about showing what that actually is because there's a few different options. Like it could be whatever the actual source of H plus was. Like maybe if it was sulfuric acid, then maybe like the sulfuric acid's conjugate base could come back in and get a proton back. But more likely it'd either be the OH group from like another molecule holding onto it temporarily, or maybe even like the epoxide from another molecule would swoop in, get this H, and then like go through the reaction itself. So yeah, there's options, and that's a lot of the time why we don't bother getting into details because it doesn't matter too much. And then I think I saw your hand, and then I'll get to you. So.
I just didn't see why the 5 carbon was included in that ring there.
5 oxygen, you mean? Or?
Is that that's the oxygen number.
Yeah. Sorry, that's a little vaguely placed. There we go. Okay. Welcome. Okay.
When you open up that epoxide ring,
Mm-hmm.
how do you know that it's that bond that's breaking instead of like the one?
Yep, so same reason over here. When we're in positive charged or acidic conditions, we go for the more substituted carbon. And the same thing here, out of the 2 carbons of the epoxide, this left one, the one I've got a number 1 label on, is more substituted than the outer end. So that's why we pick this more substituted carbon here. That's going to flip when we start looking at part B later on though. Mm-hmm.
But when you're breaking that bond from like that 1 carbon to the OH,
Uh-huh.
how do you know it's that bond that breaks instead of like the 1 to the lower carbon?
Yep, well, so this carbon has a new set of electrons coming in, and so if it wants to continue obeying the octet rule, it has to let go of something that it's got on there. So it's sort of like an SN2-like step where something's coming in, backside attacking this carbon, which is then forced to drop whatever it's holding onto as the easiest breaking bond. Uh-huh.
Why does it drop like the bonds to the OH instead of its bonds to the carbon?
Oh, sorry, you're asking about this bond versus this bond? So if I did kick that out that way, let me actually draw a box for how that might look up here. So then I would have an attachment onto, crap, I don't know if I left enough room. Let me go down here, actually. Okay, so I think that's what you're asking, right? Why break the CO bond instead of the CC bond? Yeah, so if we show that happening, something should jump out at you pretty quickly as like looking definitely not right. Okay, so we go OH attacks here, we kick out the bond to C, and then we get, oh wait, we got 5-member ring still going on. So, okay, and so now we've got this carbon has a bond to an OH plus, which has a bond to a CH2 minus. So this definitely should not look as stable as the other option where everything has neutral charges out at that end of the molecule. Plus, I guess another way to reason out of like even getting to the point where you would draw this step is out of these two, like oxygen looks like a much better leaving group. It's got a positive charge on it. So if we kick electrons towards the more positive charge thing, then things will more likely end up as neutral atoms in the next step, if that makes sense. So, okay, good question though. Definitely like doesn't hurt to go through other hypotheticals and see like, okay, if that did happen, how would it look, and is that a good enough reason to explain why things don't go that way? So, okay, so other questions about this? Uh-huh.
Is it like, do we need to show anything deprotonating that oxygen?
This one, no, if you want, you could show like another ROH or like another epoxide from a different molecule coming in, but leaving it vague like I've got there is totally fine. And I think, yeah, that's how I have it in the key as well. So, yeah. Yeah, so ambiguous deprotonation, in other words, is totally fine. But if you do specifically show something that is coming in for the proton, then make sure it's something that at least makes sense. Like you wouldn't want to stick a proton on something that's not at all interested in picking it up. So. Yep. Uh-huh.
Would it ever be like the HSO4 that did the deprotonating?
Hypothetically, yes. It's probably less likely than like the other OH or the epoxide from another molecule. But yeah, if that was like the only thing you had left around, then it would probably come pick it up some of the time. So. Uh-huh.
In the simpler example, where your ray looks like, can you just talk stereochemistry real quick?
Oh, yeah. So I guess I didn't really show any stereochem on this one, but so when this ring opening attack happens, it's a backside attack, so stereochemistry would flip. So in other words, if I had a bold bond going to the epoxide here, then I would have a dash bond like coming off of here to the oxygen afterwards. So it's just going to be like an SN2 like step, but yeah. Right, and in this case, it ends up like not mattering in the slightest anyway because it's CH2, so it's not asymmetric anyway. So, yeah. Okay, so any other questions about part A before we look at part B for contrast? Okay, cool. Okay, so B, same starting molecule. Oh, actually one thing that we can double check just to make sure we're on the right footing here is the formula that I give for the product. So C10H18O2, looks like we got 6, 7, 8, 9, 10 carbons, 2 oxygens, and 2 degrees of unsaturation. So we should have 22H, we got 18. Yeah, we got 2 degrees of unsat. Okay, so yep, that structure works for that formula. Okay, so okay, so for this one, again, you might be unsure of exactly how you want to start this one off. I guess there are actually a couple different possibilities that could happen here, but we can rule these out based on the formula that we're given for the product. So again, we might want to sort of do a simpler version of these conditions, but with the same functional groups, and sort of use that as a guide for like how we're going to tackle this thing. So again, we show some kind of thing like this. NaOH, and then H2O, for example. Okay, so you might be thinking, looking at this initially, that, well, actually, hold on. I'll get there in a second. Okay, so we know basic conditions, it goes less substituted or more substituted on the carbon that it attacks? Less, right? Good. Okay, so that attacks here. Which gets us this, which then has to protonate itself from whatever solvents around. Okay, so that gets us to here. The problem is if we try doing exactly this thing onto this starting molecule, which I think a lot of people on last year's final did, so that looks fine. We attack the less substituted carbon, kick that up. So that gets us to here. And once we protonate from the water again, I guess like I didn't explicitly write water as a reagent. You could also say like maybe it's taking it from another like alcohol group or something else in the molecule, but you can be vague about that as well. But that would get us to here. The problem is, does that match the formula that we're given? Right, yeah, it doesn't. We've got one too many oxygens and one too few degrees of unsaturation. So looking at this, we're going to have to try something different. So you should be suspecting that, okay, I'm probably going to have to use the oxygen, the OH group that's already in the molecule, and do some sort of like swinging over, making a new ring, and simultaneously opening the epoxide. So in other words, let's see if we can use the OH group in the molecule to make a new ring in this thing. Okay, so we're in basic conditions. We can't protonate the epoxide first. But what we can do is deprotonate the OH group here, turn this into a good nucleophile that can then go ring open the epoxide. Okay, so if this gets its H taken away first, okay, so we're still in basic conditions. It's still under steric control. This is still going to go for the less substituted carbon, which means, again, we probably want a number. 1, 2, 3, 4, 5. And oxygen is atom 6. So we got two 6-membered rings joined by a corner. And sticking with the numbers 6, 5, 4, 3, 2, 1. Which carbon is my former epoxide oxygen attached to at this point? 2, right? Yep. So I just have, so carbon 2 is the only one that still has its bond intact to that epoxide oxygen, which is now negative charge because it just got booted out as a leaving group. Okay, so then just to finish this up, I would need whatever protic source I have around to neutralize the charge on that O- group to get me to here. Okay, so even if you look at this and you don't really know for sure how to start tackling it, I guess the take-home like test-taking strategy on this is like try going through a simpler mechanism on molecules that you do know and then see if you can like use that as a framework to build up stuff that you would expect on your molecule. And then if that doesn't work based on other information that you have, maybe try tweaking things a little bit so that it's still following the same general pattern, just there's maybe something else doing that job.
Anytime that we see the OH minus or the H plus, can we just assume that there's water also there?
Yeah, I think like, especially for B, really that's on me for failing to write it on the arrow, but yeah, that's an okay assumption to make. Welcome. Okay, so other questions about that problem or, yep.
The first mechanism is not wrong. It's just wrong in the case that the product it asked for, right?
Exactly, yeah, so it's just saying, like you could have formed some of this molecule, but circumstances are such that we know that whatever the major product is, it happens to have like C10H18O2. So the only way to get that is from here. But yeah, if I hadn't given you that information, probably the correct structure to draw would have been this one up here. That's like more in line, I guess, with what we would normally expect. Okay. So any other questions about, yeah.
This is a different question. It's a quick question. I just want to make sure I understand that tosylation and all those agents, if you will, are just to make OH a good leaving group.
Exactly,
Right?
yeah.
So it turns an alcohol into a regular alkene.
Yeah, or you could do substitution, yeah. So yeah, it basically like turns an alcohol into just an alkyl halide for the time being, and then you can go a lot of places from there. So, yep,
So for the example in the basic conditions that you showed, it was the first step just turning the OH into a nucleophile, and then just going through the normal.
Yep, yeah, exactly. So it's still pretty much the same mechanism. It's just we do one extra step to like switch which group is doing the actual job kind of at that point, yeah. And I guess like one thing you may want to run this through like a quick sanity check is this acid-base step reasonable? Like would OH minus actually come take a proton off of an ROH? And the answer is yeah, these are probably like pretty overlapping in pK values. So there's nothing like inherently against this step happening. So,
Is there ever any circumstances where you can't use the OH that's attached to do an attack?
Yeah, I guess like so any cases where for whatever steric reasons like this one couldn't reach over to whichever carbon it was supposed to attack and like get over there. So like most commonly you would probably see that in like ring structures where their freedom's really limited. So maybe maybe if instead of having the epoxide be on this like freely movable chain thing out at one end of the molecule, maybe if I had like OH over here and like an epoxide over here, maybe it would be really hard for this to like reach over and attack either carbon, and so that would sort of rule this out from trying the same thing. Yeah?
On some of the tests, there's a reaction involving OH groups and this reagent HIO4.
We skipped that one. Yeah, so you're, Yep. I saw someone fist bump, yeah. Okay. All right, so I guess any questions about this, or do you guys want to move on to something different? Yeah?
I just was wondering if we're going to be tested on oxidation of methyl at the end of chapter 10.
No, all the stuff that we skipped in lecture is not fair game for our exam. So, yeah.
For again the stereochemistry, if it were asymmetric, does it flip also on the carbon?
Yeah, whichever one gets attacked is always going to be by an SN2-like mechanism. Yeah. Okay. Cool. So who wants to pick the next question we look at? Yeah.
I don't have a specific question, but I was wondering if you could go over organometallics on epoxides.
Sure. Yeah, I did sort of wedge this in real quick at the end of lecture on Wednesday. So yeah, actually, would you guys want to do a synthesis question that uses these? Because I feel like that's a better way to apply it. Here we go. Okay, so 2018 final number 3A. Okay, so I'm looking at this thing. I need to figure out some way of turning this into that. So the immediate thing that jumps out at me here is I'm trying to make a new carbon-carbon bond. So the bond that I'm going to have to form at some point during the synthesis is this one here from the ring onto these two new carbons that show up. So pretty much the only good generalizable way that I've learned how to do that is with cuprates and epoxides. Okay, so also looking at this, I know that if you guys remember that, wedging this in somewhere, okay, let's do it here. The pattern for like working backwards on these is whatever R group that you have from the cuprate is always going to be 2 carbons away from the OH of the epoxide. All right, so we can recognize this like there was a cuprate involved kind of thing from having like whatever disconnect be 2 carbons away from an OH group. So we don't have any OH groups on this deal, but we have something that we can make very easily from an OH group, which is the bromine here, right? So maybe at some point in the past, rather than being a bromine on there, maybe this molecule looked like this at a previous point. Okay, so can we go from, I guess I sort of telegraphed my answer by like drawing it this close in, but can we go from OH to BR here in one step? Yeah. What are some ways I could do that? Yep, yeah, I'm hearing a few people say tosylate. That's like a good sort of default one. In this case, it turns out we can get away with something even easier, and so like either PBr3 or HBr, it turns out, would also work okay, although you might risk a little bit of acid catalyzed weirdness. So you could do tosyl chloride and pyridine and then sodium bromide to swap it out. Either one of those options would work. If you're doing tosyl chloride, you probably should draw out the tosylated as its own intermediate instead of like combining steps like this. Okay, cool. So now that I'm sort of showing this thing as like the immediate after effects of cuprate plus epoxide, I can actually work backwards and break this thing into the actual cuprate and the epoxide. Okay, so I know left side, is that going to come from the cuprate or from the epoxide? Left half? Yeah. Yeah, so this half is the part that doesn't end up with the oxygen in it. So this half is from the cuprate. And then this part used to be the epoxide half, which I can tell because that OH there is the O that used to be part of the like actual epoxide ring. So in other words, I could work backwards and say, okay, that's my epoxide that I brought in. And here's my cuprate. And then just because this is the way cuprates work, I have 2 copies of whatever R group is on there. I didn't get a chance to talk about this in lecture, but cuprates are actually a little bit wasteful. Once you stick 2 copies of your R group onto the cuprate, you can only get one of them back off to do whatever reaction. So there's ways to work around that by like having what are called dummy ligands that are sort of the one that stays on copper all the time, and then like you only have to put on 1 copy of the thing that you want and you can get that back off pretty easily. But as far as we're concerned, this is totally fine. Okay, so our R group here is attached to copper. It comes in, it attacks the epoxide here, which by the way you'll note only has the 2 carbons and nothing else in it. We don't even have to worry about more versus less substituted. It pops the ring open, and then we would have to do a workup afterwards, H3O plus workup. That's WKP. Sorry about my handwriting. I just made it worse. Okay, and so that gets us the addition product over there with our new carbon-carbon bond.
What's the workup?
So just like a later step where you combine this stuff first and then like afterwards you bring in H3O plus. And we know it's got to be a second step that's done separately, because if we brought in H3O plus at the same time as all this, cuprate's not going to bother going for the epoxide. It'll just take a proton. So, yes, or so it looks like the way I have it on the key is, so this is the only part that's actually coming from my starting material. And so the epoxide itself could be brought in on the arrow as just like we're going to introduce this, but it's going to become part of the molecule in the next step. So how I actually have it on the exam key is just bring in the epoxide that I want to add it to, and then water and acid to work it up as a second step. Okay, so this is also a totally fine way of doing it. Even though we're sort of used to, like, in this chapter, seeing epoxides as like the thing before the arrow, because that's the reagent that we're starting with, it is also like the same reaction if we show things the other way around and have the copper be before the arrow. So, okay, yeah.
Why are you drawing those like dots in the line for like separating the OH?
So yeah, this is like what's called a retrosynthetic disconnect. Basically think of it as like bonds were made or broken here at some point during the synthesis. So we know that whatever is going on during this whole thing, like this bond here is the one that had to be formed during it because it wasn't there in the first place. Okay, so other questions about where I've gotten so far?
Can you show the mechanism for this step, how you would get?
Let me hop over to here actually. Okay, so the mechanism, all right, so the textbook more or less shows it the same as for Grignards and organolithiums for the time being. It turns out that's not 100% accurate. There's some other weird transition metal stuff going on, but at least as far as it's likely to come up for us so far, and I'm going to draw the two copies of the R group out separately here. For the time being, we can more or less show it the same as if this were a Grignard or a lithium. Basically just the carbon comes off the metal and goes straight in for the attack on whatever else is around. Exactly, yeah. Yeah, so this one's deliberately set up so you don't have to worry about more versus less substituted. Okay, and then at this point it sits around with its extra carbon-carbon oxygen group on there that it's just added until you bring in water and acid together. Which will give it the extra hydrogen on there, or the proton. Okay. So any other questions about this step here, which is kind of the key thing of putting it together?
So, if it wasn't just two carbons, would you have an extra like methyl or ethyl group off the epoxide?
Exactly, yeah. So I could have had an epoxide with more R groups on there, but at that point I would also have to make sure that I'm actually attacking like the less substituted carbon. If it were something where I'd have to make it by attacking the more substituted carbon, then I'm in trouble because we don't know how to do that. Like, you can't have acidic circumstances with a cuprate at the same time. So,
This is a basic.
Yep.
Does the template have to have the two rings, or did you pick that as R?
Well, so we know that, I guess for one thing, like this R group is what's going to have to attack the epoxide, so that's going to have to be what's on the cuprate. And for the other part of it, we know that this is our starting material, so probably like the R group that we use is going to have to become the cuprate at some point when we sort of bridge this gap in. Sorry? Yes, you could make a cuprate out of it, but then like whatever group that you're attacking the epoxide with might not give you this particular product is the problem. So I guess like that would be kind of a dick move to set up a synthesis problem where I'm like giving you an R group that you totally can't use in making the final product. So.
Kind of like a different situation, like could the R group be just like
Yeah, so that would work totally fine. So if we had, say, like methyl and methyl on the copper, and like an epoxide like this, it would still come off the same way, but then we'd get like this, and then you'd stick a proton on there. So basically, like whatever R group you've got 2 of on the copper is what's going to end up on this, like 2 carbons away from the oxygen position. Mm-hmm. Okay, yeah.
What causes the other ring to leave off the cuprate?
What causes this one to leave?
Like the one that doesn't get included.
Oh, so I think what causes it to stay on the copper the whole time is just like if it left, copper would have a +2 charge. I guess another way to think of it is like the first one comes off pretty easily because it's leaving behind a copper that's relatively stable. The second one is a lot harder to get off of there. So.
Well, I mean, like the one on the top left, like why does that one pop off of there? Why is it not like still included in the
Oh, well, so you're breaking this bond, so it's sort of like this bit is going off and joining the epoxide, and then like this whole chunk stays together and is just a waste product, unfortunately. So we're like wasting this entire copy of the molecule, and we only keep like half of what was attached to the copper. Yep. Mm-hmm.
So the 2 R groups on the cuprate always have to be the same R group?
To the extent that we've covered it, yes. If you get really fancy, then no. Yeah. Okay. So any more questions about this key step of the synthesis? Yeah?
Sorry, not about this step.
Mm-hmm. Okay, so I might finish up like just the last couple bits working backwards, and then we can look at the whole thing if that works for people. Okay. So then I guess the last question is, how do we actually get from the starting material to the cuprate? Okay, so do you guys remember what reagent I need to make the cuprate from? Or like what kind of functional group? So it's pretty similar to this, except I need just a lithium on there instead of the copper. So if I can convert this into the alkyl lithium, and then I can bring in copper iodide, for example, and THF. Get 2 copies of it stuck on there. Okay, so then I just have to actually make the alkyl lithium reagent in the first place, which is just going to be lithium and probably THF. Okay, so then from here, I can just sort of do the last 2 steps. Let me write it all down in one place just so it's all together. But then I would bring in the epoxide, including a workup, which gets me to here. And then the last step would get me to here. Okay. So any other questions about that one? Mm-hmm.
Could you explain where the HBr, like for that last step right there, why would you pick one over the other versus PBr3?
Oh, in this case, there's really nothing to like require you to go one way or the other. HBr would be fine, PBr3 would be fine, tosylation and then swapping it out would be fine. Out of the 3 options, I guess like PBr3 is pretty quick and easy to write, and also like HBr makes me a little bit nervous because it messes with a lot of functional groups. So PBr3 is kind of my default for like this OH goes to Br kind of choice.
Are there any like signs that we should not be using a certain?
Yes, so like we know this is something that goes by an SN2-like mechanism for part of it, and so this happens to be primary alcohol. If we were trying to do like a tertiary somewhere else on the molecule, that would immediately rule out PBr3 as an option. And in that case, we'd probably have to go either with HBr, so long as there's nothing else sensitive to it on the molecule, or tosylate, and then we could start looking at maybe trying to do SN1. So, okay. Yeah. Yes, good question. So we know the main reason we introduced cuprates is because Grignards and lithiums will screw with other R groups on the epoxide. Is that going to be an issue on this particular epoxide if we do it? Right, yeah. So we could totally get away with like sort of the quicker and I guess kind of shoddy or riskier version by just actually like taking the lithium and going straight in for the epoxide. It might be safer to get in the habit of using cuprates because you won't always be able to get away with that. But yeah, in this case, you could totally get away with it. So yeah. No, I guess as kind of a rule of thumb, whatever the shortest route for the synthesis is, like we have on the key, usually you can have up to about twice as many steps before you start getting penalized for like inefficiency. So long as all the steps actually work like they're supposed to and you get like the main thing that you want as the major product, then yeah, that you won't get docked if you're like a couple steps over. So. Okay, so other questions about this one?
What's like the mechanism for the first step for the lithium?
We didn't cover it because it's kind of complicated and like goes by single electron transfer. It's pretty much just like know that the lithium swaps out for the bromine. So.
It's not like the same. I was just confused if it was the like organolithium. Why is the bromine really?
Oh, so you're also, we don't bother to show it most of the time, but you're also getting lithium bromide as a byproduct. So that's actually why you might sometimes see this written as like 2 equivalents of lithium because technically one goes with the carbon and one goes with the bromine. But remember that anything you write on the arrow is assumed to be in excess unless we say otherwise. So you can just write lithium and it's assumed that you'll have as much of it as you need to do whatever's going to happen.
I don't know if you can answer this, but in general for these synthesis, like stepwise equations, will they have like 4 or 5 steps usually?
For the tool set of reactions that we've covered so far, yeah, like probably, I don't know, what's the longest I got on here? Yeah, probably like 6-ish is about the longest I can get before I start running out of things that I can actually have you guys do. You know, as you go through OChem 2, it's going to get longer and longer potentially, but yeah, that's kind of a good ballpark estimate for now. Okay. So do you guys want to do some more synthesis practice? Because I feel like that's kind of a useful way to put everything together. Okay. Maybe can I run through like B, C, and D of this problem as well? So, okay, cool. Okay. Okay. So, ways to start this problem. All right, so I'm looking at this and I'm thinking, okay, I've got a functional group on this central carbon. Ultimately, I need a functional group up here. Am I changing my carbon skeleton of this molecule at all by like adding or removing carbons? Right, so the carbon framework stays intact the whole time, so I'm not making any new bonds, so I probably don't need to resort to like cuprate plus epoxide stuff. I'm also not breaking any bonds. I think last year a lot of people saw this double bond oxygen and immediately thought ozonolysis, and then they tried to like get like a double bond going on here and then hit it with ozone. The problem is that's going to lop off a carbon and make the chain one shorter than you were expecting. So that's not really what we're going for. Fortunately, we now know other ways of making double bond O's other than just by ozonolysis, which requires us to cut the framework or cut the skeleton a bit. So we now know that we can make carbonyls like this from oxidizing OH groups, which we just covered towards the end of chapter 10. So I'm going to erase this bad example here. Okay, so maybe the precursor to this one, like the step immediately before the end of the synthesis, involved like an OH group getting oxidized up to this carbonyl here. Okay, so which kind of oxidizer would I want to use for that step? Yeah, PCC, good. And why can't I use one of the stronger oxidizers here? Exactly, yeah. So right now what I'm trying to make is an aldehyde. There's still a hydrogen on here. If I used a stronger one like CrO3, an acid or whatever, I would overshoot the oxidation level. I would go up to an OH here, a carboxylic acid. Yeah, so because we're starting with a primary alcohol, in other words, we got to be careful and make sure we're going just to the level that we're aiming for. Okay, good. So now you're looking at this and you're like, okay, this is actually fairly in line with like what we started seeing for synthesis at the end of chapter 9, where it's just, oh, we've got a functional group here, we need a functional group up here, maybe we can try like eliminating and then adding in a few times and like walk it over down to this end of the molecule.
Sorry,
That's okay.
related to the Jones reagents.
Mm-hmm.
So the other two Jones reagents, why is that one of them adds an OH and the other one like just doesn't?
Yeah. So a big part of the difference between them actually is like whether there's water around, because PCC like turns out that the whole reason it does what it does is it's just able to react in the absence of water. So I sort of put this in the notes, but I didn't actually like talk about it in lecture at all. It turns out if you do get to an aldehyde here, if you have water around, and acid at the same time speeds it up as a catalyst, you're actually going to do this briefly. It's reversible. So where the equilibrium lies actually depends on a few things that we'll look at in like OChem 2 whenever you take that like next semester with whoever. But it turns out having water around actually turns this into like two OH groups temporarily. And now you're looking at sort of like there's an OH group, there's an H. This thing is going to get oxidized just like it would as a normal alcohol. And so it ends up going to this. So yeah, I kind of glossed over the mechanism, but that, if you're curious, is kind of why it goes all the way to add another OH group. But this only happens if you've got water around, and PCC's whole deal is it still works when there's not water around. So. Mm-hmm.
So does the also like having the methyl coming out of it also affect it adding OH or not? Because like on in lecture you have like two different ones with the same Jones reagent. And, like one of them added OH, the other one didn't.
Oh, yeah. So pretty much like the only way you can oxidize is by pulling H's off of that carbon. And so like if I had, let me draw a separate box. So here, even with water and acid around, I could still do the same thing, make this like double OH thing coming off. But the problem is now there's no way to oxidize this because there's no H's to pull off. And so I'm maxed out at 2 bonds to O at that point unless I can figure out a way to start breaking carbon-carbon bonds. So, okay. Does that sort of answer?
Yeah, so just OH. I mean, just a O.
Yeah, exactly. So like as soon as it's away from the water and acid, it'll revert to this form too. Yeah. Okay. So yeah, that's kind of what's going on with why PCC is different from the other oxidizers, and PDC as well. Okay. So I guess any other questions about that step before we sort of tie into the rest of the synthesis? Okay, cool. All right, so now we're just looking at, let's do like elimination and addition and get things where we want them to. Okay. So if I'm trying to make an alkene here, so it's an elimination, is it Zaitsev or anti-Zaitsev, or doesn't matter? Yeah, it doesn't matter. Like all 3 directions from here are actually symmetrical, so it doesn't even matter whether I go like a double bond here or here or here. It's still all the same molecule. I'm just going to show it going upwards so that it matches how the thing's drawn over here though. Okay, so elimination on bromine. So I can actually go either good nucleophile or poor nucleophile. It's not like I have to worry about SN2 happening because this is a tertiary. Yeah, I think on the arrow I just say like any strong base. Would work just fine to make E2 happen here. Note that I am avoiding weak bases because that's likely to put me into, for a tertiary alkyl halide like this, that'll put me into a SN1-E1 mix. And I'd rather keep this simple and go E2 only so I don't have to worry about substitution products getting mixed up in there. Okay. So now I want to continue sort of moving my functional group along the molecule. Remember, bromine is a pretty convenient placeholder because I can add it either Markovnikov or anti-Markovnikov, and then I can eliminate it back off pretty easily. Okay, so am I going Markovnikov or anti-Markovnikov here? Anti. So what reagents do I need? Good, yep, HBr and peroxides. HBr, ROR, or there's a few other initiators that'll also do the job, but that's kind of the one we've used the most. Okay, so we add anti-Markovnikov, get the bromine here. We're still 1 carbon away from where we want our functional group to be, so we're going to have to do that trick again. Eliminate and then add in. Okay, Zaitsev or anti-Zaitsev? Anti-Zaitsev. So which base am I going to want to use for this? Terbutoxide, nice. And you can be kind of vague about the solvent or the counterion. I think in the key, yeah, I just say the base without any solvent. Okay, so that gets me to here. It's E2 only. It's anti-Zaitsev, so perfect. That gives me this alkene. And then to add back into that, Markovnikov or anti-Markovnikov? Anti. So what reagents am I going to use for this? Yep, hydroboration oxidation. So step 1, BH3. Step 2, base, water, hydrogen peroxide. Okay, and then the last step, once I get the OH out at the end carbon, is just oxidize it up to an aldehyde like that. And that gets me my finished product. Okay, so for this one, there's actually not a whole lot of new material after chapter 9. I guess like PCC is the only reaction that is brand new out of this whole thing.
Could you use terbutoxide for both elimination steps?
Oh yeah, definitely. So terbutoxide would be would work just fine for this.
Would the double bond in either case not be, I can't think, resonance? Would it go throughout the molecule with resonance, or is that primary?
So that's only if you can like have multiple double bonds. Because you got to have like some pi carbon framework to like move those electrons and like slide them around the molecule. If all you've got is the one alkene, then pretty much it's just locked down in that place and there's not much else it can do. Yeah. Okay. Other questions about this one?
You have terbutoxide and LDA.
Mm-hmm.
Are those the same, like they do the same thing?
Yeah, like LDA is a little bit stronger with a higher pKa, so it may potentially like screw up other functional groups on the molecule that we won't see until later. So terbutoxide is probably the safer way to go, but yeah, for now, like LDA is also just like totally interchangeable with this. Mm-hmm. Uh-huh.
What's the base that you would use if you were trying to go Zaitsev? So you use like OH- and
Yeah, yeah, so like any strong base, good nucleophile, so like any, pretty much any non-bulky like OR- would be a good choice too. Yeah. Okay. So any other questions about part B here? Okay, cool. You guys cool with going on to part C? Okay. Okay. So So this one, it's pretty immediately obvious that we're going to have to cut a carbon-carbon bond somewhere because we're starting with a ring and we're ending with some kind of linear thing. Best way of cutting carbon-carbon bonds that we know of right now is going to be ozonolysis. So we're going to have to figure out how to make that work. Okay, so that should be the first thought that pops into your head looking at overall what is going on here. Okay, so this actually looks like something that's like fresh out of the ozonolysis step, like the direct result of an ozonolysis. So maybe let's try sticking it back together and see if we can use that as a guide for like what else might need to happen. Okay, so in other words, the two carbons that end up double bonded to oxygen, this is going to look real weird, but actually I'll redraw it down here. So those two carbons must initially have been double bonded to each other. So like something like that, although let's redraw that as an actual sensible looking ring. So we got carbons 1, 2, 3, 4, 5, and 6. So we must have initially had a 6-membered ring with carbon number 1, 2, 3, 4, 5, 6. Carbon number 1 has a methyl on it, and carbon number 6 could have gotten that OH during ozonolysis. If we're careful about which ozonolysis type we do. Okay, so if I wanted to go from here to here, I would do step 1, O3. What am I going to use for step 2? Yep. Water, preferably with peroxides in there just to speed it up. Okay, so that's kind of like the first way that I'm going to start tackling this thing is just by like, okay, ozonolysis is a pretty likely candidate here. What would this look like before the ozonolysis happened? And that gets me to here, and that already is starting to look pretty similar to our starting material. So that sort of is making progress in the like reverse direction towards the starting material. Okay, so any questions about figuring that part out? Yeah. So we didn't cover that, but yeah, there's a few oxidizers. I guess I mentioned like KMNO4 is like not a great choice out of the strong oxidizers because it'll actually go for carbon-carbon double bonds. So yeah, there are a few like older school ways of splitting this, but ozonolysis is probably the easiest way to do it, and it's the only one that we've covered too. So yeah, I guess if you guys are like studying off of other exams and you do actually do something that would work, that's totally fine on the exam, but for now I'll probably stick to the ones that I covered so far. So, okay, cool. So now let's figure out how to sort of close the loop on this one. Okay, so I need an alkene here as part of the ring. Can I get an alkene right away in one step from where I'm starting? Yeah, I see people shaking their heads, and they're correct. Yeah, there's no way to like start with just an alkane and get to an alkene. In fact, we're extremely limited in our options for what to do on this starting material because it's like it's got nothing. It's just all single bonds. What is the one thing that we can do to that molecule, however? Yep, good. Radical halogenation is like my only option for a starting point here. Okay, so let's give that a shot. Br2H nu. Where's my bromine going to end up? Whoops, that's 6-membered. Bromine's going to end up on the most substituted carbon, so like that, which is good because that's actually a perfect location for where we want the alkene to go in the next step. Okay, so then getting from here, let me draw like a little bubble around this so it's sort of closed off. Okay, there we go. So getting from my alkyl halide over there to this alkene here looks like pretty much just a regular elimination. Do I want to go Zaitsev or anti-Zaitsev? Zaitsev, yep. Yeah, I want to substitute, want to eliminate to the more substituted carbon, not this less substituted methyl up here. Okay, so Zaitsev means pretty much any strong base, good nucleophile. What do I have on the key? Oh. So methoxide would be totally fine and good. Any kind of alkoxide or like OH minus would also work great, or a few other options. Okay, so then that gets us the alkene, which we can immediately snip apart and get that final product that we want. Okay, any questions about that? Okay, cool. So let's also do D because it's another useful way of looking at epoxides and cuprates. All right, so it even has the same starting material as A. But I'll scoot this up a bit. Okay. So we're looking at this final product, and we're looking for an OH group and then a carbon and a new sort of R group after that point. So the new carbon-carbon bond that we're making during this reaction is going to have to be across here. So looking at this, we've got disconnect carbon-carbon OH, which tells me that in this case, probably the left half of the molecule came from an epoxide. Because it's the one that ends up with the OH afterwards. And so the right half must have been from a cuprate or more generally some kind of organometallic. Okay, so now we just got to get it set up for that to work. Okay, so this looks like the immediate after effect of like cuprate plus epoxide. It's got the OH still on there. So maybe, I'm going to go out this way. Easiest way to show it is just, here is my epoxide, and then here's my cuprate. Okay. So, so this half from the epoxide is obviously related to my starting material in some way. It's got a 5-membered ring. Since I'm just rolling up with this cuprate with like 3 carbons on it, or 2 groups of 3 carbons on it, I am actually totally okay to not show this being formed at all. I'm just bringing this in as a separate reagent that's all ready to go. So you don't have to show how to make this. Because it's not actually made from our desired starting material at all. It's just a separate piece that we show up with partway through. Okay, that's just for the cuprate. We do still have to figure out how to make that epoxide from our starting material. Okay. So how am I going to make an epoxide from that?
When you say bring it in, should we put it on an arrow or show it?
Yeah, or you can just do like plus this and like show going to the product. Either one is totally fine. So yeah. Oh, and also, sorry, I'm just realizing you can't see the bottom of the board very well. Sorry. Okay. So any other questions about how I sort of worked backwards for this part? Okay, cool. So then what functional group do I normally have if I'm trying to get to an epoxide? Like what starting material would be, or what precursor to this molecule, what functional group would it have? Alkene, yep. So I pretty much just want to have this alkene. What reagents do I use to make the epoxide? Yep, MCPBA. That gets me to there. And then alkyl halide to alkene. doesn't matter Zaitsev versus anti-Zaitsev, but I do want to make sure I'm avoiding SN2 on here, so I probably want to go terp butoxide just to be safe. So that'll get the alkene there. So this one is actually shorter and simpler than it looks. It's really only 3 steps. So make the alkene, convert it to an epoxide, and then bring in whatever cuprate to get the new R group stuck on there. Okay,
You do not show the forming the OH.
Oh, yeah, I guess you would have to include like, so like step 1 you could say cuprate, and then step 2 you could do H3O plus, just to get the workup so that you're protonating the OH group on there. Yeah, good question. Okay. Okay, any other questions about how to figure this one out? Okay, I'm going to take a couple minutes and erase this half of the board, so if you guys, oh yeah.
Could you use one of these mechanisms to go over like HOMO and LUMO?
Sure, yeah. Just as a heads up, like sometimes like it's a little bit more complicated than sort of the breakdown that we've covered so far, especially once you start getting conjugated pi systems involved. So I'll try to apply it only to cases where it's actually like fair to ask you to apply it. So. Okay. Actually, I guess I'll erase this part of the board, and then I can just like point at what I've already gotten written up there and look at which part of the molecule is doing what. Okay, so I guess for all of these steps for every mechanism, we can apply sort of a where are the electrons coming from, like the highest occupied molecular orbital versus where are they going to, the lowest unoccupied molecular orbital. So that's where we would get HOMO and LUMO from. Okay, so like for this first step, we could protonate, when we protonate the oxygen, it's the lone pairs of oxygen that's doing the attack, right? So here the HOMO is lone pair on oxygen, which you could also write as non-bonding on oxygen. And the LUMO is just an empty orbital on the hydrogen, right? At least the way that I've drawn it. Realistically, if I were going to ask you to assign or to say what the HOMO and LUMO are, I would have to probably be a little bit more detailed about where that proton's coming from. So in this case, it would be the H2 sulfur bond that actually breaks, or sorry, H to oxygen in H2SO4. Again, if I didn't draw out the structure, that would make this quite a lot harder, because then you'd have to figure out that H2SO4 actually looks like this, if you didn't already know that. And so you're breaking the HO bond and kicking out that O minus as a leaving group. Oh, I guess I didn't actually specify which orbital, so this by itself is not enough information. All right, so I'm breaking a sigma bond when I do this. So the LUMO orbital is the HO sigma star. Remember that whichever orbital or whichever bond gets broken, that means that you must have dumped electrons into the antibonding version of that orbital if you're coming in for the attack. Okay, so questions about this first step, applying the orbitals. Okay, so for this one, let me try to squeeze it in up here. So in this case, again, the atom that's doing the attack is this oxygen with its lone pairs. So lone pairs on oxygen, different oxygen than over here. Maybe I should specify lone pairs on oxygen of the epoxide versus here lone pairs on oxygen of ROH. And then the LUMO Okay, so what bond am I breaking here? I'm breaking a CO single bond, right? So CO sigma star must be what's actually getting electrons poured into it at this point. Okay, so yeah, for all this like regular 2 electrons moving at once with like a regular arrow thing, applying HOMO and LUMO is pretty much just like look at where the electrons are coming from, look at where they're going to. Often if they're going to somewhere that forces a bond to break, then that means they're going into like some sort of antibonding orbital. Okay, does that sort of address like, okay, good. So any other questions about this example? I did not move the camera before I went over here. Okay, sorry to anyone who's watching the recording, but just to bring you up to speed. Okay, so we're just looking at this epoxide ring opening reaction and applying electron source versus electron sort of sink, or what's getting attacked versus what's doing the attack. Okay,
Can you just go over why the LUMO, why that one is the antibond?
yeah, so I guess, let me come down here. Jeez. So I guess maybe if we draw like a really simple version of the MO diagram, so I guess say we're looking at the CO bond. So you got sp3 hybridization on both. Okay, so I guess as like a real quick refresher on MO theory, since we're making a single bond between the C and the O, that means we make 2 new orbitals in between them, a sigma and a sigma star. And the sigma is normally the only one that's got electrons in it when it's sitting around, because that's what sort of makes the bond favorable to exist, is giving these electrons a lower energy place to sit. But it does mean that if we bring in some more electrons from like oxygen's lone pairs coming in, we're going to dump them into this higher energy orbital, which means the bond order between C and O goes to 0 at that point. So it's just sort of, we're bringing in too many electrons, which means the bond has to stop existing, which is why the CO bond sort of gets kicked out and the ring opens when the epoxide gets attacked. So, okay, good. Any other questions about this stuff? Okay, I'm going to erase the top part of the board, and then we can have someone else pick another question to look at. Okay, who wants to pick another one for us to look at? Yeah, definitely. This mystery bottle one? Yeah, I like this one. I guess I kind of like this format because it's sort of like a working backwards kind of a puzzle. Okay, so 2018, number 2. Okay. So you found a mystery bottle labeled Luzonensin. You have no idea what it looks like, but you do know when you start messing around with it and doing hydrogenations, you get, I'm not going to bother writing that whole name out. Well, yeah, I guess this is good naming practice or working in reverse. Okay, so 2R, 6S, 6-bromo, 1,1,3, trimethyl, 2, 3, methyl pentyl, cyclohexane. Okay, there shouldn't normally be a hyphen in there. I'm just adding it because I had to split onto another line. Okay, so let's figure out what this looks like. Okay, so working backwards from the parent part of the molecule and then sticking groups on. Okay, we got a cyclohexane. So we got carbon 2. I guess just to match up with how I have it in the key, maybe let's say 1, 2, 3, 4, 5, 6. Okay, so carbon 2 has this compound group with its own substituents, so it's a 3-methyl pentyl group coming off of there. All right, so I'm going to draw the pentyl first, 1, 2, 3, 4, 5, and then 1, 2, so 3-methyl pentyl is how that group would look. Okay, so that's that. Then I got a 1,1,3 trimethyl, so 1,1,3, and then a 6-bromo. So like that. Okay, so that's my connectivity. And then I have to figure out R and S on this thing. So, all right, so carbon 2 here also has an H. I'm going to just start out by guessing that maybe the H is in the back, which makes it easier to figure out what's coming towards me because I don't have to do that fake swap thing. Okay, if I do it like this, then I've got priority 1, 2, oh wow, that's really confusing with the numbering. Okay, so priority 1, 2, 3, so I'm going R, and looks like, yes, luckily it was supposed to be 2R, so my guess just happened to get me the right answer in this case. If it had turned out to be S after I drew this in, then I could just flip bold and dash and I'd have the right stereochemistry there. Okay, so guess and check is probably the easiest way when you're drawing out the actual stereochem for a structure if you're just given like the assignment, just because there's only 2 possibilities, and if you pick the wrong one, you can flip it real easily. Okay, I'm going to start out making the same guess over here. I'm just going to start out assuming maybe my H is in back. Priority is bromine 1. This carbon is number 2. This carbon's number 3. It's bromine, so it should be S. And it looks like, yep, luckily the name wanted me to put S there. So that was fortunate. So the first guess happened to be correct on both of those assignments, but it's easy enough to fix if it turned out not to be. Okay, so any questions about that? Okay, cool. So that's what happens when you hydrogenate it. You also find out that if you take luzonensin, do tert butoxide and tert butanol, you get some alkene C15, H22. And then if you take that alkene and you hit it with ozone and then DMS, you get a whole pile of stuff. So okay, so you get this plus this plus 2 equivalents of this one, formaldehyde. Okay, so putting this whole thing back together is going to take a little bit of detective work. Let's see what we can figure out about the rest of this first and maybe make this a little bit easier to work with later on. Okay, so I guess looking at the first reaction that we did with hydrogenation, we know that that's just going to take whatever alkenes we've got in the molecule and get rid of them, convert them to single bonds, but it's not going to change the structure at all. So whatever Luzonensin looks like, it's probably looking something like this, but with some double bonds in it at some location. So Luzonensin, we already know, looks like that thing. And I'm going to redraw it a bit neater over here without all the annotations on it. Bromine bold. Do this other group bold and the methyl. Okay. And then with at least one alkene in it, possibly more, we don't know yet. Okay, so whatever Luzonensin looks like, if we take it and react it with TBUOH, what kind of, or TBUONA, I should say, what kind of reaction are we likely to do to this thing, assuming that it's permissible based on where the alkenes are? E2, right? So this, we do E2 on it. And we end up with something that's formula C15H22. So okay. So I guess first of all, terp butoxide we know favors anti-Zaitsev. So that means it's going to have to eliminate up this way. There's an even stronger reason why this is like the only good alkene location, and that is that there's no beta H's over here. Like E2 out this direction is literally impossible. So again, whatever we're doing to Luzonensin, whatever it looked like in the start, we do an E2, make a new double bond out here. So again, whatever it looked like, whatever alkenes it had in it, those are still there. We just don't know which alkenes they were or how many there were yet. But we do have a formula, so we can use that to figure out what's going on. Okay, so this formula, let's figure out our degrees of unsaturation, and that might give us some tips. So right now on this molecule, we have 2 degrees of unsaturation. One for the ring, one for the pi bond, plus however many secret alkenes are in here that we don't know about yet, plus whatever the number of extra alkenes is going to be on there. Okay, based on what we're given for formula though, this should have 32 protons if it were saturated. It's only got 22, so we've got 5 degrees of unsat. So we need another 3 to get the structure to match the formula that we know we're supposed to have. So that tells us that whatever Luzonensin looked like to start with, it had 3 alkenes. And it's still got those alkenes like somewhere in this whole mess to get to like the right number of degrees of unsaturation. So next we're going to have to figure out where those go. I guess any questions so far about how I'm sort of reasoning through this? Okay, cool. Alrighty, so I guess the easiest place to go from here is maybe start looking at, can we sort of match carbons in this structure to carbons in whatever products we got in a way that makes it trackable to figure out what ended up where. And the easiest thing to do for this might be looking for methyl groups or like carbons with particular R groups on them that are a little bit distinctive. For instance, this one here has 2 methyl groups coming off of it. This is the only carbon that has 2 methyl groups coming off of it in all of the products. So I think it's a pretty safe bet. We could call this one carbon number 1. So we know that this carbon here is definitely part of an alkene if we've done E2 to form it so far, which means that this is going to end up as a CO double bond when we hit it with ozone. So I'm just going to keep the same numbering I did up here just to make it easier to track, but if this is 6, then this is also 6. Okay, and then this would be carbon 2. Let's just go around the ring and number them all while we're here. Okay, so we got 1, 2, 3, 4, 5, 6. So 1, 2, 3, 4, 5. And then 5 should also end up with a carbonyl on it because when this double bond got ozonalized, it sort of cut up the 5-6 bond. Okay, so we've identified sort of the, I guess, forensics of what this thing looked like before we hit it with ozone. Now we can figure out all the other chunks that are attached to it. So we don't have much of this group left. I guess if I want to start throwing numbers on the side groups, I could say like maybe call 7, 8, 9, 10, 11. So 2 has 7 and 8, but then it's missing 9, 10, 11 in the methyl group coming off of there as well. So that tells me that not only did this bond get chopped during ozonolysis, but also so did the 8-9 bond. So that got split during ozonolysis, which means that I've got probably like some rest of the molecule chunk out here floating around as one of my products. So maybe I could say like 9, 10, 11. Actually, no. That doesn't work though, because then 9 would have to have a methyl group coming off of it, which doesn't work. So maybe I'll go, okay, so let's label that one as 12 perhaps. So maybe if we say like 12 is the methyl, this one would be 9, and this one could be 10. So 12, 9, 10, and then the 10-11 bond also got split during this reaction, it looks like, because that's no longer on there. So that's one of these copies where maybe like one of those is carbon 11. And if we draw out both copies individually. Okay, so we've accounted for all this whole tail of the molecule. We still haven't accounted for what happened to carbon number 3 and its methyl. But we know that we have one free-floating carbon that also got split off. So maybe if we assume that bond also got broken by ozonolysis, I guess we could call this one 13. And that would be 13 as well. Okay. So there's a fair bit of sort of guess and check, but like keeping track of what ended up splitting off from what is sort of the easiest way to piece this apart, or numbering.
Not only one C double O. This is 2 equivalents.
Okay, yeah. Okay, so that's what we got so far. So we know that these are the bonds, the ones with the disconnect that got split during ozonolysis. Which is good because that tells us we needed to have 3 extra alkenes in the molecule somewhere, and we know that they must have been located here, here, and here. So actually, if we sort of redraw this thing with all of its alkenes intact, they must have been there and also up there. And so this is this alkene here that we made from doing E2. So Luzonensin itself must have looked like that, but before the E2 happened, it still had its bromine on there. There we go. Okay, oh, and that's still bolded too. Okay. So yeah, there's a lot going on in this problem, but you can sort of, it's a little bit like putting together the bits of information that you have and sort of working backwards and then figuring out what happened to this thing after it got split into a bunch of pieces. Whew. Okay, so other questions about this one? Mm-hmm. Mm-hmm. Yeah, it chops across every double bond in that case. So we're just assuming that ozone is present in excess, so there's enough of it to do all of the alkenes at once. Mm-hmm. Uh-huh. Yeah, so I guess like I start looking for sort of which areas of this molecule look like a decent match for which areas of this molecule, and like the only, I guess like a quaternary carbon like this where it's got 4 other bonds to C is sometimes a good place to start because it can't actually do much in the way of reactions, like it can't have had a double bond on there, so it couldn't have done any like ozonolysis. So that was sort of where I started like looking for like matches between the product and the starting material. And then I can sort of work my way around like, okay, I know this is a ring of 6 carbons, so it probably stayed mostly together. It looks like I've got 1, 2, 3, 4, 5 still attached, and then 5 was once looped back around to 6, so that would have been my ring. And then it's just sort of like working out where all the splits to other groups coming off of the ring ended up being, and then like throwing the alkenes in those locations. Mm-hmm. Yeah. Mm-hmm. 5, sure. Real quick before we move on, any last questions about this one? Okay, sweet. Okay. Okay, so 2018, number 5. Okay, so this one is saying we take a molecule that looks like this. Oh, you know what? This is not actually fair game for us because I didn't cover making epoxide rings by any other methods than MCPBA. So I can go through it, but I think, yeah, this would not be fair game for you guys. So yeah, I guess thumbs up or raise your hand if you still want me to cover it anyway. No, okay. A lot of people shaking heads. Okay. What else would you guys like to look at instead? Uh-huh. Same exam? Oh, yeah. Okay. Okay, so this one just asks for mechanism and products. So from here, oh, I guess I give you the product actually, which is good because there's several possible things that could happen here, but since I'm telling you which one I want you to figure out the mechanism for, that really helps narrow it down. Okay, oh, and it's H2SO4. Okay, so we know that the OH group, there's pretty much nothing else in the molecule that can react at first, so easiest place to start is just pick up a proton on that OH group. Okay, so that gets us to here. And now we've got an OH group that can detach as a good leaving group pretty easily. Quick sanity check. How stable is the carbocation that it leaves behind? Like pretty stable, right? Yeah, it's tertiary. So that step looks pretty okay. Like it's still a carbocation, but it's at least a pretty decent one. Okay, so that gets us to here. We know that, so there's no reason for this to rearrange in terms of like getting to a better like tertiary carbocation because it is already tertiary. But we can still do rearrangements if there's something that energetically favors it. So for example, like going to a more stable ring size would still give this thing motivation to rearrange. We also know, given that the product is a 5-membered ring, we're going to have to do some sort of ring expansion reaction because there's no other way to make that happen. So if we show the arrow pushing for that rearrangement, it's basically going to look like this bond breaks because this entire carbon here picks its electrons up out of the bond and hops over onto there. So it's mainly just driven by like 4-membered rings being a lot less stable than 5-membered. So even though the carbocation itself is going from tertiary to tertiary, it's still getting like a big energy boost from allowing the ring to relax kind of. So, okay, so just to double check that that is actually going tertiary. Okay, so we've got a couple different ways to show this. Easiest way, if you're not sure where to start drawing on this, is straight up just redraw the molecule exactly the same, erase one of the bonds, and redraw it in for where the ring carbon is now shifted over to. Okay, so that actually doesn't give us a tertiary carbocation, that gives us a secondary. That might be kind of disfavorable actually, because secondary is not as good as tertiary, but presumably the energy it gained from going from 4 to 5-membered ring was enough to make up for it to make this a feasible step. Okay, so we can redraw this as our new 5-membered ring. But if it can, it's going to try to get to where it has both a tertiary and a 5-membered ring. So we can do one more rearrangement. We don't have any H's to move, but we do have a methyl group that we can slide over. And that'll get us to here. Okay, so we knew that something like that was probably going to have to happen anyway because we start out with both methyls on the same carbon and end up with them on neighboring carbons. So at some point we're going to have to do some sort of methyl shift. Okay, so that gets us to here. And now we've got everything's happy, it's tertiary and it's 5-membered ring. So the last thing that's going to happen is we can finish up this E1-like step. If you want, you can show like HSO4 minus coming in for the proton, but you don't have to. But you do have to form a double bond between them eventually. Uh-huh.
So can you go over again why it's more favorable to expand the ring and move the carbocation?
So in this step here, you're going from the 4 to the 5-membered ring. So like the ring size is inherently more stable. The moving the carbocation just sort of happens as a consequence of like this carbon here is the one that's losing a bond. So it would end up with a positive charge here. Unfortunately, that makes it secondary, which is not great. But fortunately, it can like fix that by immediately having another shift, moving a methyl over. Yeah, so I guess I think the group that actually did this reaction and found this product like is like, yeah, it looks a little bit unlikely, but it's favorable enough, especially since it can immediately stop being secondary in the very next step. So, yeah. Okay. So any other questions about this one? So it's more or less acid catalyzed E1. You just do some fancy looking rearrangements in the middle, and then it finishes up the E1 at the end.
Yeah, that last part, anytime there's like a carbon cation, and nearby hydrogen will always just use that bond.
Sometimes. So in this case, we know pretty much that we have to make an alkene in the product, which means that this is probably going to have to be an E1-like reaction. But if I hadn't given you an alkene, we know that E1 and SN1 often occurs in mixtures. So I could just as easily have said, like, maybe when it gets to this point, maybe instead of an H falling off and U wrapping up as E1, SN1 could just as easily have happened, which would get you to, like, maybe if there's water around, water could stick on, or whatever weak nucleophile you've got. The only reason we're not showing SN1 is because the product that we tell you to show has an alkene in it. Yeah, exactly. So really, we don't know like which one's going to be more favorable. Like temperature is sort of a good way to control it. Like higher temperature favors elimination. So if we were like deliberately heating this up, probably this would be the better outcome. Yeah. But there's also like a whole bunch of other possible products based on like maybe the carbocation rearrangement never happens in the first place, and you just do an E1 on this as it exists right now. So yeah. So in this case, I would have to give you like which specific product I'm interested in, because otherwise there's a whole bunch of stuff you could get. Okay. How much time we got left? Oh, wow. Okay. So in the like 15 minutes or so we still have, actually I'm going to erase this side of the board and then we can go over one or two more questions. Okie doke. Who wants to pick the next problem? No? Uh-huh.
I just have a question about that one. Do you have to show the little like bond breaking, the little carbon-carbon bond breaking?
When you do the rearrangement? So you don't really have to show the disconnect. I just drew it in there for like explanation purposes. But yeah, like as soon as you show the arrow coming out of this bond, it's implied that this bond is going to cease existing because those electrons just get spent making the new bond instead. Yeah. Okay. Other questions? Yeah. Mm-hmm. Yeah, and really, like I didn't explicitly write H2O on the arrow, so you could just easily have said like HSO4 minus, since that's the only thing that you know for sure is like still around. That like that's going to come take the H. But yeah, like, or it could be the OH group from another molecule that's just starting to go through this reaction itself is probably the most likely outcome actually. Yeah. Okay. Other questions? Uh-huh.
Yeah, for one thing, for when you're making epoxides,
Mm-hmm.
you know how like for like the RLI H3O,
Mm-hmm.
you said that's only for like the beta hydrogen?
Yeah, so it's pretty much like, here, let me draw it up here. So,
How would you use that on the exam? Like what
yeah, so I guess in other words, when you can get away with RLI or RMGBR, so organolithiums or grignards on epoxides, pretty much the limit is no beta hydrogens allowed. So this one would work okay because there's no other carbons coming off at all. Or if you've got groups that don't have any hydrogens at the beta carbon, so like a terp-butyl would be okay. Or like an aromatic ring would be okay. Basically like anything where there's no H's at those positions. So those are pretty much the only times when these are safe to use on an epoxide. The rest of the time you want to use a cuprate. Yeah, so if you want, like you can also like use a cuprate on these as well. It's just you have options with these. But I guess like if you are trying to attack an epoxide, cuprates are pretty much guaranteed to work. So that might be the safer one to get in the habit of using. Okay. Yeah, so you can sort of, like the cuprate is one more step. So if you want to like, if you were doing this in an actual lab, you would probably just go for it with the organolithium instead of bothering to make the cuprate. But yeah, most of the time, like these reagents are going to cause you problems. Okay. Any other questions about those ones? No, I skipped that in lecture, so you guys are off the hook for that. So, yep. Okay. Any other questions, or do you guys want to break early? Yeah.
As far as like the content on the final, is it mostly the newer stuff? Or just comprehensive?
Good question. So you guys know it's 200 points, right? So the way I think of it is like a 100-point midterm exam on the new material matched up with a 100-point cumulative exam. So it's going to be about half and half new versus old material. Yeah, it might not be split cleanly. Like each problem might have like a mixture of new and old stuff on like different parts of it, but I'm going for about half-ish of the points like for each type of thing. Yeah. Yeah.
Could you do some example of oxidation on like a big molecule where you have to pick like a
Oh, yeah, definitely. Okay, so maybe something like this. Let me get tricky and actually show. Okay. So if I gave you something like this, I guess probably the first thing you want to do is go through and figure out, like for each OH group, is it primary, secondary, or tertiary? Because that'll limit its options. So this one is tertiary, this one's secondary, this one's primary. Okay. So if I ask you to say, make this out of it. So tertiary is not going to react whatever we do because we don't have any way to get any of the carbons off there to make more room for oxygen. Secondary, it's only got one thing it can do if it gets oxidized, and that is go to this ketone carbonyl that I've shown here. Primary is pretty much like the bigger differentiator between what oxidizer you want to use. So in this case, I'm only going from 1 bond to oxygen up to 2 bonds to oxygen. So what kind of oxidizer would I want for that? PCC, good, yep. Whereas if I hit this with Jones, the only difference between products, so tertiary still doesn't react, secondary still reacts the same, but primary is the only way you can tell that something has changed because primary can oxidize one step further if you hit it with Jones-like conditions. Okay. So does that kind of address what you were looking for? Okay, cool. Mm-hmm. Yeah, for the time being. Like later on, we'll see more options for how to oxidize stuff, but that's all we need for now. Mm-hmm.
So if you're just
Yeah, and it won't make any difference to the outcome. It'll still just go to the same ketone either way. Yep. Uh-huh.
Will we have to ever like write out like the actual Jones reagent, or can we just say Jones?
You can say Jones, but you should be able to recognize all the other like possible combinations that do the same thing. So just look for like chromium 6 with some acid and water around, in other words. Yep. Okay. Other questions about that? Yeah.
So just being able to know if something is oxidized or reduced,
Mm-hmm.
how would we, like, just looking at the past example, any questions?
Yeah, actually,
Been reduced or added?
yeah, maybe let's do a couple of those if people are okay with that. So like 2018 number 4. So this is not just predict the products, it's also describe whether the thing that's happening to the organic molecule is oxidation, reduction, or neither. Let me just sort of pick a few at random from here. Okay, so you got alkene, and it gives you Br2, CH3OH. Okay, so first of all, this is like predicting the products is something out of chapters 4 and 5. This is all alkene reactions. So we know that we're going to get a bromine on one carbon and an OCH3 on the other. Okay, so looking at this, this carbon down here has a new bond to a more electronegative atom. So this carbon got oxidized. And this one up here also has a new bond to a new electronegative atom. That's also gotten oxidized. Oh, hey. So both carbons got oxidized. This is overall an oxidation. Okay. So maybe one more example and then we can break. Are you doing an exam review in here at 11?
Yeah,
or?
I've already booked the room.
Okay, sorry. I'll be out of your way in just a second. Okay, so maybe the same alkene, if we hit it with O3 and then water, just to redraw it in the space I have here. Okay, so aside from the obviously larger number of oxygens that are in here now, we can go through each of the 2 carbons that got changed. This one is oxidized. This one is also oxidized. So overall, this reaction would be an oxidation. Okay, so I guess any questions on this before I wrap it up? Okay, cool. So yeah, if you want, there's several problems like this in the exam archive. So like going through and looking at what changes on each carbon is kind of good practice. All right, aside from that, I'll probably be in my office on and off for most of the rest of today, and then Monday, Tuesday next week, and then I will see you guys at the exam on Wednesday morning.